Many gases can be produced in small amounts in the laboratory. Gases are usually measured in terms of their volumes rather than their masses. In this lesson, you will learn what the molar volumes of gases are at standard temperature and pressure, STP, as well as at room temperature and pressure, RTP. You will also find out about Avogadro'S Law and how to determine the molar mass of a substance from experimental values. Finally, you will learn how to apply what you have learned to calculate the masses or volumes of reagents needed for a chemical reaction. A balloon has to be filled with hydrogen using the apparatus shown. The balloon takes about 2 cubic decimeters of gas before bursting. Using the reaction between zinc and hydrochloric acid to make the hydrogen, find out how much zinc will be needed. Assume an excess of acid will be used. First, click on the molometer to close the molometer. Then, correctly balance the equation for the reaction by filling in the spaces. The equation then shows the number of moles of hydrogen that 1 mole of zinc would produce. Enter these numbers on the next line. Click on molometer and enter 1 in the column next to zinc. The molometer will then tell you the mass of 1 mole of zinc. Answer: 65 grams. What mass of hydrogen will be formed from this mass of zinc? Answer: 2 grams. Enter the masses on the next line. But is the volume of this mass of hydrogen enough to fill the balloon? In the next exercise, you can test it to find out. You are now going to investigate how much zinc to use to fill the balloon. Select 65 grams for the mass of zinc and start the reaction. Wait and see what happens. The balloon has been filled up with too much hydrogen. Test some other masses until you succeed in just filling the balloon to capacity. What is the correct mass of zinc to use? Answer: 6.5 grams. How many moles of zinc was this? Answer: 0.10 mole. How many moles of hydrogen were produced? Answer: 0.10 mole. What is the approximate volume of 1 mole of hydrogen gas? Answer: 20 cubic decimeters. Gases are most easily measured by volume, but we need to be careful about the conditions when the measurement is done. Each balloon shown here contains the same amount of a gas. Change the temperature and the pressure using the sliders and watch what happens to the size of the balloons. Note that the volume of a fixed amount of gas varies with the temperature and pressure. When we measure the volumes of gases, we need to state the conditions of temperature and pressure at which these volumes were measured. Two sets of temperature and pressure conditions are normally used. The most common is standard temperature and pressure, STP. Click STP to see what these conditions are. The other set of conditions is room temperature and pressure, RTP. Click RTP to see what these conditions are. Under which of these conditions would a given amount of gas have the greatest volume? Answer: RTP. Summary: the volume of gas produced in a chemical reaction depends on the amounts of the reactants used and the equation for the reaction. Gases are more easily measured by volume than by weighing. The volume of a given amount of gas depends on the temperature and the pressure. To compare amounts of gases by volume, they must be measured under the same standard conditions of pressure and temperature. You are going to compare two common gases, hydrogen and carbon dioxide. The same apparatus and an excess of acid will be used each time. First, look at hydrogen. Balance the equation for the reaction above, which produces hydrogen using magnesium. Enter the value into each box. Use the equation and the molometer to complete the ratios by mole and by mass for magnesium and hydrogen. The mass of magnesium to be used has been chosen for you, 0.24 grams. Enter the mass of hydrogen gas expected. Now, work out the number of moles of magnesium and hydrogen involved and enter the values. Now look at carbon dioxide. Balance the equation for the reaction above, which produces carbon dioxide, CO2, from marble chips, CaCO3, and acid. An excess of acid is used once again. Use the equation and the molometer to complete the ratios by mole and by mass for CaCO3 and CO2. The mass of CaCO3 to be used has been chosen for you, 1.0 gram. Enter the mass of CO2 expected. Now, work out the number of moles of each of these substances and enter the values. Click Start to see the reactions. When they have stopped, fill in the tables. Are the masses of the gases collected the same? Answer: no. Are the volumes of the gases collected the same? Answer: yes, the same. Answer: yes. What does this tell you about the relationship between the volumes of these two gases and the number of gas molecules they contain? Answer: as equal volumes of these gases contain an equal number of moles, they must contain an equal number of gas molecules. This was the conclusion Avogadro came to nearly 200 years ago after studying many gases. Click on Avogadro's law to see the law he discovered. The result that follows from Avogadro's law is that 1 mole of gas molecules should have the same volume whatever the gas. The volume of 1 mole of gas is called its molar volume. The small balloons of hydrogen and carbon dioxide above each contain 0.01 mole of gas. Their volumes are both 243 cubic centimeters at RTP. How many times bigger would a balloon containing 1 mole of gas molecules be under the same conditions? Answer: 100 times. Click on Inflate to expand the balloons to contain 1 mole of gas each. What is the volume of each balloon containing 1 mole of gas? Click on Molar Volume to check your answer. Answer: 24,000 cubic centimeters. What is the mass of hydrogen in the balloon? Answer: 0.02 grams. What is the mass of carbon dioxide in the balloon? Answer: 0.44 grams. Summary: under the same conditions of temperature and pressure, equal volumes of different gases contain the same number of moles of gas. Therefore, equal volumes of different gases under the same conditions contain equal numbers of gas molecules. Gases all have the same molar volume under the same conditions, 22.4 cubic decimeters at STP and 24 cubic decimeters at RTP.